In Lesson 12 of the fast.ai course, Part 2, we are introduced to the mean shift clustering algorithm. And in this video, I'm going to walk through the implementation. The mean shift clustering algorithm is based on this idea of weighted average, where every point in every update, you take the weighted average of the points around it, and closer points have a larger weight, farther away points have lower weights. And then you update the position of that point based on that average. And you continue this number of update steps for all points until your points converge to the centroid of the given cluster. So the algorithm is explained as follows in the lesson. For each data point x in the sample big X, find the distance between that point and every other point. Create weights for each point in big X by using the Gaussian kernel of that point's distance to X. This weighting approach penalizes points further away from X. The rate at which the weights fall to 0 is determined by the bandwidth, which is the standard deviation of the Gaussian. And then we update X as the weighted average of all other points in X, weighted based on the previous step. So I've tried to visualize this here, where the red point is the point X in question, and then these blue points that are dark blue are weighted higher because they're closer, and we get lighter and lighter shades of blue the farther away we get, because the weight decreases the farther away you get. Okay, so first thing we have to do is we have to create some fake data, and we want to create the data in a way that it's knowingly clustered around a set of centroids. So we're going to reverse engineer the clusters based on the centroids. So we're going to have 6 clusters, and we're going to have 250 data points in each of those 6 clusters for a total of 1,500 data points. I create some random centroids, and these are XY coordinates, and there are 6 of them. And we're going to create data using PyTorch's multivariate normal, which creates a multivariate normal, also called Gaussian distribution, parameterized by a mean vector and a covariance matrix. The covariance matrix in our case is this diagonal matrix with 5s down the diagonal. And the mean vector is m, which in our case is going to be the centroid. And then we take a number of samples from that distribution, which in our case is 250. So looking at this covariance matrix, I asked Gemini to explain what the main takeaway should be, and it gave me 3. First is no correlation. The 2 variables are uncorrelated. The covariance is 0 on the off diagonals. For a multivariate normal distribution, this implies they are independent. Both variables have the same variance of 5.0. And if used in a 2D multivariate normal distribution, this will produce a circular cloud of data points equally spread along both the x and y axes. So I'm going to take my first coordinate pair of my centroids, and I'm going to pass it through here and get a sample. So now I have 250 coordinates of x and y data point. I'm going to plot this and make sure the aspect ratio is equal so it looks square. So we can kind of see this is, a circular graph. You can see that the density of the points is higher the closer we are to the centroid, and the further away we get, the density is much less. So I'm going to run this sample, or call this sample method for each of my 6 centroids, concatenate the samples so I get a single data set with 1,500 coordinates, each with an x and y value. I'm going to plot this data. So for each centroid, I'm going to plot the samples for that centroid, and then I'm going to plot the centroid itself with a marker of x, so I can visualize where these clusters should converge on with my algorithm. So these are my 6 clusters, and then I have my centroids designated by these x values, and we'll see that as the mean shift clustering algorithm updates each step, the clusters all kind of collapse and converge at the centroid. All right, so first thing is done. We have data, and we have it's kind of contrived in a way that we know it's going to cluster around these legitimate centroids. All right, cool. So first thing we're going to do is we're going to talk about how we're going to create these weights for our weighted average. And the main idea is that the farther away you get from the point, the more the weight decays, or the lesser the value of the weight is. And how that weight decays is going to be a variable that we set. So we're going to use the Gaussian distribution, and you can see it in code here, or you can see it in math here. Here we have x minus mu. In our case, we have distance d between one point and another point. Here we have sigma squared and sigma squared here. Instead, we have bandwidth, bw. And the main idea here for bandwidth is that as the bandwidth increases, the distribution flattens out. So the weights decay slower as distance increases. So if we look at the two extremes, when I have a bandwidth of 1.0, my zero distance point, so the point that I'm considering, has a weight of 0.4. As soon as we go 2 units away, this drops all the way down to 0.05. All right, so we have an 8x drop, or 8x difference. Whereas if we look at for a bandwidth of 10.0, I'm about 0.04, where the distance is 0, and I'm just shy of 0.04 when the distance is 10. So it's a lot more uniform of a distribution because the standard deviation is very high. So this is a parameter you can tweak based on what makes sense for your data, or maybe just testing out different values to see what makes sense for your data. We can also use a simpler linear function. So we have negative d, which is the distance, plus I, which is a kind of like a hyperparameter. We're going to clamp the minimum value to 0. So that means the value of negative d plus I cannot go below 0. And if it does, it replaces it with 0. And then we're going to divide by I here. So I was asking Gemini some ways to think about it. And it said mathematically, this calculates the maximum between 0 and I minus d over I. And if we divide these two values by I, we get 0 and 1 minus d over I. So let's take a look at the actual chart. We can see that the y-axis is 1.0, which makes sense. That's what we see here, 1 minus d over I. And we can see that the x-axis, or the d-intercept, is whatever the I value is. So here it's 3, here it's 8, here it's 12. And the main takeaway for me here is that similar to bandwidth, as I increases, the slope decreases and the weights decay slower as the distance increases. So these are two different weight distributions that we are going to potentially use. Okay, so we have some data and we have a way to calculate our weights. And so now we can step into the process of implementing the full algorithm. So I've taken out the 3 main points about the algorithm. So for each data point x in the sample big X, find the distance between that point and every other point in X. So I'm going to call this d is some function of the point in question minus all of the points in big X. We then create weights for each point in big X by using the Gaussian kernel of that point's distance to X. So our weights is equal to the Gaussian given the input of these distances. And then we update X as the weighted average of all other points in big X, weighted based on the previous step. So X is some weighted average function which takes in the weights and takes in the data points X. Okay, so that is a snapshot of our algorithm. Because we're going to update the data after each step of the algorithm, we're going to clone the data to start. The first value is the first coordinate, which is 29.764, comma 26.161. I'm I'm going to look at the shapes of x, big X and small x. Big X is 1500 by 2. Small x is a single point, so it's just 2 elements. What we want to do now is we want to calculate the distance between that point x and every other point in big X. We're going to start by just calculating the difference, and then eventually we'll get to the Euclidean distance, so square root of x squared plus y squared. So x minus x is a legitimate operation because the dimension of 2 matches the dimension of 2, so we can broadcast this coordinate pair to all 1500 coordinate pairs. So this is going to work. Just taking a look at some of the data points, the first value of this subtraction, of this difference, is a coordinate pair of zeros. And the reason is that x is the first value, and in big X, we still have our original first value of x. So we're subtracting x minus the same value. So that gives us 0, 0. Then in the next case, we're taking x minus the second point. So we get 1.292 and negative 4.333, so on and so forth, down 1500 rows. We don't want just the difference, we want the distance. So the next step is to square that difference. So I can do that just as a element-wise operation. And if we take a look at these values, we can see that this is 6.26 squared is about 40. 3.03 squared is about 9, and so on. And then finally, we can sum across the columns. So across the columns is across the second dimension, which is at index 1. And so we get x squared plus y squared. So now if we look at this, this is 0 plus 0 is 0. 1.6 plus 18 gives us 20. 4.9 plus 9 is 14, and so on. And finally, to calculate the distance, we take the square root of the sum of squares. So the square root of 20 is 4.5, square root of 14 is 3.7, so on and so forth. So because we're performing element-wise multiplication, which is here, followed by a summation, we can use ein sum. So I'm going to do that here. I'm going to have ij and ij as the two shapes because they are the same value. And the second dimension, which is the dimension of 2, is going to go away because we're going to sum across that dimension after performing the element-wise multiplication. So if we run that, we're going to get the same value as we have here. We can also use matrix multiplication, but if I understand correctly, you have to take the values from the matrix's diagonal to get the element-wise product between x minus x and x minus x. So if we look at the shapes of x minus x and x minus x transpose, we can see that the inner dimensions match, so we can do matrix multiplication. But the result is we get a 1500 by 1500 matrix. So if we just take the diagonal of that matrix, we're going to get the element-wise multiplication, or the element-wise product of the values in x minus x times the values in x minus x. And then of course we can take the square root to get our final distance. So there's 3 different ways to achieve the same result, and we'll see that throughout this implementation there's always going to be element-wise multiplication with a sum, ein sum, and then a matrix multiplication that all give you the same result. Okay, cool. So now we have our distances. So the next thing is we create weights for each point in big X by using the Gaussian kernel of that point's distance to x. So I just pass my distance through my Gaussian function, and I get 1500 weights. And now we go on to the last step. We want to update x as the weighted average of all other points in x, weighted based on the previous step. So what we're going to do is we're going to take the element-wise product of weights by x, because we want each coordinate, the x and y coordinate, in big X to be multiplied by the weight. And then we're going to sum down the rows, so we get 2 final coordinates. And then we're going to divide by the sum of the weights, so we get our weighted average. So this is the first time we run into a situation where we can't just perform multiplication because the dimensions are not compatible. So weight has the last dimension of 1500. X has a last dimension of 2, so that is not compatible. What is compatible with 2 is the dimension of 1. So if we pop on a unit axis at the end of weight, then we can broadcast that to each of the coordinates in our data set and perform element-wise multiplication. So that is exactly what we're going to do here. We're going to add a dimension to weight, and now we can perform element-wise multiplication. So this first weight, 0.16, is going to multiply by the first coordinate pair in x, and that result is 4.75 and 4.175. This gives us two columns of weighted coordinates, and we're going to sum down the columns to get a single pair of coordinates. So this is the numerator of the weighted average. And another way to think about this is if we didn't apply that unit axis, we could only do an element-wise operation between weight and the first coordinate, or first column, and then we take the sum, and then the weight times the second column, or the second coordinate, and the sum, and we see that we get the same value here as we do here. Okay, so that's the numerator, and now we're going to calculate the denominator, which is weight.sum, and then we're going to divide the numerator by the denominator, and now we get our weighted average point. So this is one update for 1 point. Okay, so let's wrap this up into a function called oneUpdate, except now we're going to go through all of our data points. We're going to calculate the distance between that given point and all the points in big X. We're going to get the weight for those distances. And then we're going to calculate the weighted average, and we're going to update our original data, xi. And so that's why before we start doing this iteration, we clone the data so we don't lose our original data set. So if I run this here and I run oneUpdate, the first value is now what we calculated up here, 28.1 and 27.6. So that's oneUpdate. We want to do multiple updates so that we get closer and closer to converging to the centroid of the clusters, or of each cluster. So we're going to now wrap this into a mean shift function. I'm going to take some data, I'm going to clone it, I'm going to iterate through however many steps I want to do, by default 5. I'm going to perform the update for that step, so I'm going to take the weighted average of all other points for each point, and then I'm going to return x, and this is going to take about 1.5 seconds on the CPU. In this case, it was 1.09. If we run it again, get 1.12. Yeah, so it's a bit faster for now, or I guess there's some variance. 1.33. Well, I was trying to get 1.5 because that's what I was getting before this, but oh, I guess so, 1.4. Anyway, it doesn't matter. It's about 1 to 2 seconds. Okay, so let's look at now our updated data. Just as a note, every time I ran this, it was cloning the data fresh. So, I was starting with the original data and then performing 5 steps. So if I now plot the centroids here, I'm going to set the alpha value so that it's less than 1, so that I can see the converged points sitting behind centroid x's. And so we can see our algorithm is successful. Our clusters have converged to the centroid, and they are very close to the actual centroid values that we picked at the start. So we can see that, okay, this works. It took 5 steps, took 1.5 seconds. That's great. Can we make this faster? And the answer is going to be yes. But before we do that, I want to show the animation that we create in the lesson, because it's just very visually appealing to see this kind of gravity of the cluster collapsing into the centroid. So I'm not going to play it. I'm just going to go frame by frame. And by the third step, we're almost there, right? There's a couple of stragglers here and there. By the fourth step, it's pretty much done. And then by the fifth step, there's probably some minor adjustments. So yeah, very cool to see this visually, very pleasing, satisfying to see how these clusters collapse into centroids. So as I mentioned, this takes 1.5 seconds. Can we do this faster? And the answer, of course, is yes, if we can run this on the GPU. And how can we run this on the GPU? And to maximize the parallelism in the GPU, we want to do this in batches. And so doing this in batches is going to require us to alter the algorithm because now the shapes of our tensors are going to be different. So instead of updating one data point at a time, which is what we've done here in this for loop, what if we update one batch at a time? So we're going to start with a batch size of 5. And right off the bat, we are going to run into issues. So we want to calculate the distance, then we want to calculate the weights, and then we want to calculate the weighted average. So when we calculate the distance, the first step is taking the difference between the point in question and all of the other points in the data set, big X. Except now, in this case, we don't just have a single point, we have a batch of 5 pairs of coordinates. So this subtraction is not going to work. So first, what I'm going to do is we're just going to make it work with the dimensions, and then I'm going to show a visual that I made to try to understand, why these particular dimensions work. So we know that when in doubt, if you can get a unit axis, it can broadcast to any other integer dimension. So I'm going to add a unit axis at the start of my x coordinate or coordinate pair. And then I'm going to insert a unit axis in the middle as the second dimension for my data set. So now this one broadcasts to 1500, this one broadcasts to 5, and 2 broadcasts to 2. So now if we perform our difference, well, we get a successful final result. We get 1500 rows, each of which contains a set of 5 coordinate pairs. So I'm just going to look at the first coordinate pair, which is the first item in the batch. So we take 0 as the first index. I'm going to subtract all the points from that first point. And then I'm going to see that is that first point difference the same as the difference that I have with my full broadcasted version. So what I'm taking here is I'm taking all 1500 rows and I'm taking all 2 columns, but instead of all 5 items in the batch, I'm taking the first one, and indeed that is equal to this difference that we did manually. So that's just like a quick sanity check to make sure that the broadcasted difference is working correctly. All right, so let's dig a little bit deeper into why we added the unit axis. So if we look at x and then we look at x indexing into it with none, visually there's not a lot of cues, but we can see that this additional unit axis comes with another pair of brackets. And so how I kind of visualize that or understand that is that it's kind of grouping the items into one dimension, and it's grouping it so that we can now broadcast that to any number of dimensions that we want. When we add the unit axis to the second dimension of our big X, it's a little more clear or kind of visually intuitive that we see that we have an extra pair of brackets around each pair of coordinates. So we are allowing each pair of coordinates to be able to be broadcasted to any number of dimensions. So I took some time to visualize this, and this really helped me understand, how broadcasting works and really how to think about a 3D tensor. So this additional dimension here we'll get to in a second. In this graphic, we're focused on this additional dimension around these coordinate pairs. And what this additional dimension does is that we can copy over this pair 5 times, once for each value in this batch, and then we can perform subtraction, right? So x none minus x colon comma none. And we subtract first pair minus this pair, and we get 0. Second pair minus the first pair is negative 1.29 and 4.3. Third pair minus that first pair is this third row here, and so on and so forth. So this was a visualized way of seeing how the additional dimension allows broadcasting, because we can copy over this pair of coordinates across the batch, right? So that's one direction of broadcasting. On the flip side, we now have an additional dimension here around our batch, and that lets us copy over the batch to every single one of these pairs so that it allows that previous X pair to batch item pair broadcasting so that we can do subtraction in groups of 5. And one idea or one takeaway I had from this whole exercise is that, I used to think of 3D tensors as a cube, which in some cases makes sense if you think about like an image like 128 by 128 by 3. Thinking of that as a cube does make sense. But in this setting, I thought it was easier, it was more intuitive to not think of a 3D tensor as a cube, but to think of a 3D tensor as a grouped 2D tensor. So we have 1500 rows and we have 2 columns, but in each row we have groups of 5 values. So that's kind of, another kind of, I guess, kind of learning tool that I took away from this experiment. Okay, so again, just to recap, we can copy over this batch 1500 times, and then we can copy over this pair of coordinates 5 times, and this pair 5 times, and the third pair 5 times. So it's kind of this like two-way broadcasting that is allowing these groups of 5 differences to be generated. All right, let's keep moving. So now I can wrap this in a function. So instead of my distance, I'm going to have batch distance. So I'm going to have x with the unit axis added to the front, and then we're going to have big X, the full data set, with the unit axis added to the middle. Take the subtraction of them, square them. We're now going to sum across the last dimension, and then we're going to take the square root. And the last dimension is the 2 coordinate pairs. So if I run this, the shape I get is 1500, and which is the number of rows, and we have 5, which is the number of columns. So let's take a minute to understand what this means. The first row contains the distances between the first coordinate pair in big X and each of the coordinate pairs in the batch. The second row is the distance between the second coordinate pair in big X and each of the batch coordinate pairs. Then we have the third coordinate pair, which each of the batch, so on and so forth until we get to the 1500th coordinate pair and the distance to the 0th, first, second, third, fourth item in the batch. Cool. So we can pass this into our Gaussian and we get back matrix tensor of weights. And I'm just going to look at the first 5 weights, and we can see that we have a square matrix because the weights between the first 5 points, the points in our batch, are the same across the points. So here we have, this is the distance from the first coordinate in the batch and the first coordinate pair in the data set, which is 0.016. We can see that we also have the same 0.016 value, which is for between the second coordinate and the second coordinate, so a distance difference of 0. We put that in the Gaussian and we get a 0.16. So the diagonals are all 0.16. And then the difference between the first item in the batch and second coordinate pair in our data set is the same as the difference between the second item in the batch and the first coordinate pair in our data set, big X. So for the first 5 values, we have a square matrix. And then once we get to, the row 6, we would have the weights from these 5 points to the 6th coordinate pair in the data set and the 7th coordinate pair all the way down to 1500. So technically, if we had a batch size of 1500, the weights in full would be a square matrix. But in this case, we don't have a batch size of 1500, we have a batch size of 5. Okay, so we have our weights, and we did that because we got our distances. We got our distances in a batched way, which required us to understand a little bit more about broadcasting. Now we get to the part where we have to understand broadcasting a little better again. And this is because we have to perform the weighted average. So I'm just going to take a sip of water real quick. And the weighted average starts with an element-wise multiplication between the weights and the data points. And then we're going to take a summation down the columns to get coordinate pairs. So mathematically, this is not how the shapes are going to line up, but just conceptually, this is what I'm dealing with. I have my weights, where the first column is the first batch items weights with all the 1500 points. The second column is the second batch items weights corresponding to the 1500 points, and the third and the fourth and the fifth and so on. So I'm just showing an example for the first two batches. So for the first batch item, I want to take my weights, multiply them by all of my data points, x coordinate, and then take those weights, multiply it by all the coordinates in the y coordinate, so the second coordinate in my data set, second column. And then I want to take a summation of those element-wise products, and I get my x coordinate weighted. I haven't divided it yet by the sum. And then I add these down here, and I get my y coordinate. I have dot sum here. It's actually, no, never mind. The dot sum is correct. What I don't have here is dividing by the sum of weights, which would actually give us the final coordinates. But this idea is that we have this like column values here, element-wise with a column of values here. We sum down the column and we get our final weighted value here. For the second item in our batch, we do the same thing, except now we're going to generate our second item of weighted coordinates. So this is conceptually what I want to implement. But as we can see, the shapes don't really line up right now, which is why we're going to have to do some broadcasting. So let's look at the shapes we're dealing with. Our weight matrix is 1500 rows by 5 columns. Our data set is 1500 rows by 2 columns. So obviously 2 and 5 are not compatible, they're not divisible. So we need to introduce a unit axis in such a way that we broadcast the 5 batch items to each of the 1500 coordinate pairs. So we're going to start by just making the dimensions work, and then we will make sure we understand the result, and then we'll kind of do another visual to look at it. So what I'm going to do is I'm going to add a unit axis at the end for my weights, and then I'm going to add a unit axis in the middle for my data set coordinate pairs. So what this means is now each of these weights can be broadcasted to both coordinates. I can broadcast these coordinates to each item in the batch, and 1500 and 1500 are already matching, and so that's in alignment. So if I perform the element-wise product, I'm going to get a resulting tensor that's 1500 rows, 2 columns, and then each row has 5 items in the batch. Okay. Next step is we perform, after our element-wise product, we perform a summation, and we perform it down our rows of, or I guess down across our rows, or down our columns, and we get now 5 pairs of coordinates. And then we're going to divide that by the total weight sum, and we'll get our weighted average. Okay, so let's get a little more intuition, and we'll see it in the visual, because this was a kind of a nuanced point that I didn't quite understand the first time I looked at this. So let's look at the first pair of coordinates that we get. And again, these are not yet divided by the, they're not normalized by the weights, so to speak. So these coordinates are the sum of the first pair of element-wise products in each set of 5 batched items in each of the 1500 rows. So let's visualize this here. So what I'm doing is I'm taking all 1500 values, I'm taking both columns, but in each row, I'm taking the first item in that group of 5 that we see. So let's see if we can visualize this first by code and then with my visual. All right, so we run this. Okay, great. So what do we get here? We get 4.75 and 4.175. That's the first item of the first row. All right, so here's the first row. And we're taking the first item because we're concerned about the first item in the batch. Next, we have 0.886 and 0.948. That is, again, the first item of the next row. The first item of the next row should be 1.42 and 1.196, which it is, and so on and so forth. So if we take the sum of this kind of, skipping down the rows, just taking the first pair of coordinates, we get our value of 296.88, comma 291.612, which is what we had up here. So this was a key part of my understanding, is that when we're actually summing down these 1500 rows, it's summing all the first batch items together, and then all the second batch items, and then all the third batch items, and all the fourth, and all the fifth. So that's how we get our 5 coordinates. So looking at this visually, what do I have here? I have my weight matrix that is broadcasted, that has a unit axis, so it can be broadcasted. And it has 1500 rows, and it has 1 column, and each row has 5 elements corresponding to the 5 items in the batch. I have my dataset big X with the unit axis in the middle, so I have this additional set of brackets, and that's going to allow me to broadcast this across these 1500 for each batch item at a time. So what I'm doing here is I'm broadcasting this single coordinate pair to all 1500 of these weights. The first item times each of these coordinates, because the dimension of 1 broadcasts to 2, gives me 4.75 and 4.175. The first item of the second row of 5 items multiplied by my first coordinate pair gives me the second item here. The first item of the third row times the coordinate pair gives me the third coordinate pair here. That's my weighted pair, and so on and so forth. And then once I do that element-wise product, I do dot sum across the 1500 dimension. That actually sums together every first item in each row, and that gives me the first coordinate pair. If I was to look at every second item, so 0.926 plus 4.544 plus 0.054 plus, I would get this 476.489 and 514.066. If I was to add up the third item in each of the 1500 rows, I would get my third coordinate pair, weighted. Fourth item in each row, fourth coordinate pair, fifth item in each row, fifth coordinate pair. So this was, again, another kind of piece of the puzzle in broadcasting that I hadn't really seen before visually. And so this kind of unlocked my understanding of how you sort of have this aligned kind of grouped aligned calculations that you can perform with all the first items and all the second items and all the third items. And you can kind of imagine how this could translate to other kind of problems of, batching data together. Okay, so that's how we get our weighted coordinates. I assign that to this tensor called numerator, and just checking that the values are what they should be, which they are. And because we're performing an element-wise multiplication followed by a sum, we can use einsum, we can use matrix multiplication. So here I have 1500, 5, and then I have 1500, 2, I'm not including 1500 in the result because that's the dimension I want to sum across. So my result is going to be 5, comma 2. And if I run that, I do indeed get the same 5 coordinate pairs. I can do the matrix multiplication with a transpose so that dimensions align accordingly, and that gives me the same result. And finally, I can divide by the sum of weights. Here I have to transpose it so it's in the right dimension, so I can broadcast this single unit axis across both pairs of coordinate axes in my numerator. And we get our final weighted average single update points. So the first 5 points in our data set have now been updated, and we've done it in a batched way so we can utilize our GPU. So we're going to need a new mean shift function where I'm going to now iterate the number of steps, which is 5, and instead of iterating through every single point in big X, I'm now going to iterate through the batches. And I'm going to take a slice with the starting and end point of the batch. I'm going to pluck that out from my big X, so that's going to be my little x batch, calculate the batch distance, calculate the Gaussian, calculate the denominator, and then calculate the weighted sum, or sorry, the average. And just a reminder that we are replacing values in place. So that's why we're cloning our data. Okay, we are almost there. I put my data on the GPU. And if I run this, I can see that it now takes, 6.5 milliseconds, sometimes going even lower. So using the GPU, we cut the execution time from 1.5 seconds down to 6 milliseconds, which is a 250x speed up, which is awesome. And the only reason we could do this is if we batched our data. So if I run this here, I'll see that now I get the same result as my sequential CPU calculations, where my clusters have converged to the centroids. And if I performed an unbatched calculation, so we're going to go back to the original mean shift CPU implementation. So we're going to run that. And I'm going to see that I'm not really going to get any speed up. So if I don't batch my data, I don't get the benefit of GPU parallelism. So that is it for this video. This quickly turned into a broadcasting exercise, and the most time I spent preparing this blog post / video was in creating those visuals and really understanding how those different shapes interact with each other to allow broadcasting to happen, and what do they actually mean. What corresponds to the first batch, what corresponds to the first coordinate pair in big X, what corresponds to the first weight, so on and so forth. Second takeaway is that we can use broadcasting with element-wise multiplication and a summation. We can use Einstein summation, and we can use matrix multiplication interchangeably, so whichever one works better for us. And seeing kind of this relationship between the dimensions, seeing how where you add a unit axis allows you to broadcast in certain ways, and then finally seeing how a 3D tensor is better thought of as a grouped 2D tensor instead of a cube. Those were some of my main takeaways from this conceptually. And then in terms of execution, the GPU only gives you a speed up if you perform batch operations on it. So that's it for this video. Thank you so much for watching. Please like, comment, and subscribe, and I will see you next time.